Okay, so 10 to the power of x. So again, when you are graphing a function, you get to pick x, and then you simplify to figure out y. So again, you can just choose numbers close to 0 to make the math easy. Okay, so when x is -2, you just substitute -2 for x. And the way we handle negative exponents is we make them positive exponents, but in the other part of the fraction. So in this case, it moves down to the denominator. Okay, so the point would be -2 comma 1/100. So that's barely above 0. Okay, -1. That simplifies to 1/10. So still not very far above 0. -1, 1/10, 4.1. Okay, 10 to the power of 0. Anything to the power of 0 equals 1. So 0 comma 1. When x is 1, y is 10 to the power of 1, which is just 10. So 1 comma 10. And when x is 2, y is 10 to the power of 2. So 10 times the second 10 would be 100. Okay, so 2 comma 100. So that's way off our graph, but it tells us that as you go to the right, the graph is going up really, really quickly. Okay, so connecting up the points. On the right side, you're rapidly increasing. And then on the left, you are almost flattening out. So you never quite hit 0. You're always barely positive. So you never hit 0, you never cross to the negatives. And again, this function that for me I'm graphing in red is 10 to the power of x. So this is an exponential function. The variable is in the exponent. Okay, and so just a quick note for those who weren't here last time. This notation means the inverse of the function. So it's not the power of -1. It just means the inverse, which is sort of like the opposite. Okay, so an inverse function undoes the original function. So the original function took in a -2 and outputted a 1/100th. So the inverse undoes that. It takes that 1/100th and gives you back the original -2. So again, that's why we say an inverse undoes the action, right? The initial action turned -2 to 1/100. The inverse restores the 1/100th back into a -2, right? So you're back to what you started with. So the action has been undone. Okay, so the inverse basically switches x and y. So -1, 1/10 becomes 1/10 -1, and so on. Okay, so these would be the values for the inverse of c of x. So we'll go ahead and plot this graph as well. Okay, so we can see that this inverse function, as it goes to the right, it's going upward, right? The y values are going up, but very, very slowly. So we will draw an arrow going upwards as we go right. On the other hand, as we go to the left, you can see that the points are diving downwards. Okay, so you never quite touch the y-axis. You always stay barely to the right of it. Okay, and so what do we name this function? Okay, so if I quickly go back to the front side, right? So the inverse of the exponential function 2 to the power of x was log base 2 of x. The inverse of the exponential function 3 to the power of x was log base 3x. Okay, so this is 10 to the power of x, right? So log base 10 of x. However, 10 is obviously a very important number in our math system, right? We use what's called the base 10 number system. A lot of things in life are based on tens. So because log base 10 is used so often in real life, we actually can also just call it log x without any base, without any number here. Okay, so from now on, you'll never really see it written like this anymore with the subscript of 10. If it's written like this, you need to just be aware that there's sort of an invisible 10 here. Okay, so yeah, there's a lot of invisible numbers in math. Like for example, we know that x is really x to the invisible first power, right? Or you can have an invisible coefficient of 1. Now, square root, right? Here it's not an invisible 1, the invisible index, it's an invisible 2. So now for log, it's not an invisible 1 or an invisible 2, it's an invisible 10. Okay, so again, whenever the base of the logarithm is 10, you don't write the 10, you don't write any base at all. Okay, so you'll hear this referred to as the common log. So that basically means log base 10. Okay. All right, so there's one more that we want to go over. So for this one, we're going to need our scientific calculators. So if you could take that out. Again, if you would like to check one out, I just ask that you drop off your ID card. And again, I don't have enough for everyone, so first come, first serve. Here, you can use this one. But sorry, Adrian, I'll have to share with you because I give all mine out. I'll give it back. All right, everyone. So this next one is the letter E, and it has the exponent of x. Okay, so unlike most letters in math, E is not a variable. It's not like x, where in one problem x is 2, the next problem x is 5. E is always the same number. It's kind of like the Greek letter pi. We know pi is always about 3.14. So E is always going to be the same number. Okay, so we'll do the same x values as above. Okay, so now how you're going to type this in. Again, every calculator is a little different, so some of you may have different models. But for this type of calculator, if you look above this ln button, sort of printed above it is e to the power of x. Hopefully you can see that. So to get to that, I do second that button. And you notice it creates the exponent automatically, right? That the up arrow means exponent. The way the letter E works, it pretty much always has an exponent. Okay, so I'll just type in e to the power of -2. That's the x value. Okay, so since this one goes on forever, let's just round to the nearest hundredth. Okay, so about 0.14. Okay, so it's not exact, so I'll do the little wavy, meaning approximately. Okay, and then we'll just repeat for the other x values. Okay, so when x is -1, that'll round to 0.37 approximately. Okay, either the 0th is exactly 1. That should make sense because remember, yeah, anything to the power of 0 equals 1. Okay, so e itself, right? We know that anything to the power of 1 is itself. So e is approximately 2.7, and this will round to 2.72. And then e to the power of 2 is about 7.39. Okay, so let's go ahead and plot those points as well as we can. -2, comma 0.14, -1, 0.37, 0, 1, 1, 2.72, 2, 7.39. Okay, so as with all exponential functions, we can see that on one side it's rapidly going vertically, and on the other end it is almost going flat. Okay, and then now we're going to do the inverse of that function. So as we saw above, to get the inverse, you just switch the x and y columns. So just like the ones above, you can see that on the right side, it's slowly increasing, but on the left side, it's diving downwards. Okay, so what do we call this inverse function? Okay, so the base of the exponential function was e, so it'd be log base e of x. However, just like the log base 10 of x above, this one has a special name because it's so common in real life. So this one is, the symbol is ln x. So this is a L, not a capital I, lowercase l. Okay, so again, just like above, just saw how you never see it as log base 10x, you just see log x. From now on, you'll never see it as log base e of x. You'll see it as ln x. Okay, and so the meaning of ln, this is the natural logarithm or just natural log. Yeah, if you're wondering why it's ln and not nl for natural log, This is from like, I think Latin, where the adjective comes after the noun, kind of like in Spanish. Okay, so yeah, so these two um, types of logarithms are very, very common. So you'll need to know their hidden bases, right? When you see something like the front page, here the base is clearly 3. But you will need to know that when you don't see a base at all, it's really invisible 10. And when you see ln x, it's not invisible 10, it's invisible e. So e is Euler's number. Euler was a famous mathematician who lived centuries ago, and he discovered a lot of things. So they named this important number e after him. Okay, so before I continue, let me see if there's any questions up to this point. Okay, so we've talked about how logarithms can have different bases, right? You can have log base 2, log base 3, log base invisible 10, log base invisible e, and any positive number can be a log. You can have log base 5, log base 19, and so on. Okay, so sometimes it'll be useful to change the base of the logarithm because if you look back at your calculator, right, you've got a log button, right? So that's log 10. You've got a ln button for log base e, but there's no like log base 7 button. There's no log base 2 button. So we need a way to change other bases into either base 10 or base e. Okay, so the formula that will do that. Thank you. I go and pick up a classwork. Okay, so this is called the change of base formula. So for any log base b of a, you can rewrite it as log base c of a divided by log base c of b. Okay, so you might notice there's no c on this side, right? So where does c come from? Well, that means you get to choose c. C can be any number that you want. But the most common choice we'll do is we'll make c 10. Because remember, when c is 10, it disappears. Okay, so the more common form of this formula that we'll use is just log a over log b. Okay, so log base b of a can be rewritten as log a divided by log b. Okay, so if you look over here, log base 7 of 13, right? Most calculators don't have a log base 7 button, so you can't type it in directly. But using our new formula, we can rewrite this as, so a is the argument. Remember, that's sort of the full size number. So here, 13 is the full size number. So log base 7 of 13 can be rewritten as log 13 divided by log of b, which is the base. Okay, so with that in mind, we should now be able to use our calculators for this next section. Okay, so problem A, log base 2 of 4. Again, if you look at your calculator, you probably don't have a log base 2 button. Okay, so we can apply this change of base formula to rewrite it as log of the argument 4 divided by log of the base 2. So let me just quickly show you what that should look like. Okay, so again, log of the argument 4, and make sure you close the parentheses, and then divided by another log of the base, which was 2. Okay, so that whole thing simplifies to regular 2. Okay, so that's the first part of the problem. In each box, I'm asking you to do two things. First, evaluate the logarithm, which I already did, and then write the equation in exponential form. Okay, so if you remember last class, we saw that this logarithmic equation is basically representing this exponential equation. Okay, so over here, when we say that log base 2 of 4 equals 2, we're really saying that this 2 to the power of this exponent equals this number. Okay, so that one was a little bit confusing because the number 2 shows up twice. So let me do one more with you. Okay, so log base 7 of 343. So remember, that can be rewritten as log of the argument 343 divided by log of the base, which is 7. So typing that in. Okay, that comes out to 3. Okay, so now I would like us to rewrite this logarithmic equation as an exponential equation instead. So the base of the logarithm becomes the base of the exponential equation. It's trying to turn into the argument, which is 343. And the exponent, which allows it to do that, is 3. Okay, so that's what I mean when I say write the equation in exponential form. I want you to take the logarithm and rewrite it without the word log, but with an exponent instead. Okay. So any questions about either of those two? All right, so I'm gonna ask you to take a few minutes then and try out some of the following problems. Okay, so go ahead and give it a try and let me know if you have any questions. So log base 4 of 16, again, using the change of base formula, you could rewrite that as log of 16 over log of 4. Okay, and if you use your calculator, you'll figure out that this is 2. Okay, and then you can rewrite this by taking the base of 4. You're trying to turn it into 16, and the exponent that does that is 2. Okay, so again, you want to see how the positions of the numbers sort of relate between the two forms. Right, so again, the logarithmic equation and the exponential equation have the same 3 numbers, just sort of in different places. Okay, so this next one was a little tricky, natural log of 4. So this one, you don't have to use the change of base formula because you have an ln button, right? Natural log right here. So natural log of 4, that one's approximately 1.39. Okay, but now what about the second part of the problem? How do we write this in exponential form? So here it might be useful to remember that ln 4, natural log 4, represents log base e of 4. Okay, and then from here, again, we just take the three numbers in the problem and rearrange them. Okay, so the base is e, so that becomes the base of the exponent. It's trying to turn into 4, so that goes on the other side. And the exponent that accomplishes this is 1.39. Okay, so this statement and this statement are equivalent. It's just two different ways of saying the same thing. Okay, problem E, this one also had an invisible base, but this time, because it's log and not ln, it's invisible 10. Okay, but you don't need to do the change of base formula because you've got the common log button, right? This log really means log base 10. So if you just do log of 1000, you see that it's 3. Okay, but then from there, you can again rewrite it using the exponential form. So the base is 10. It's trying to turn into 1000. And the exponent which lets it do that is 3. Okay, and then this one you do need to use the change of base formula on. Log base 2 of 1. You could rewrite that as log of 1 over log of 2. Okay, so if you type this into your calculator, it equals 0. Okay, and now to rewrite that as an exponential equation, the base is 2. It's trying to turn into the argument of 1, and the exponent which does it is 0. Okay, so again, for all of these, the base of the logarithm becomes the base of the exponential term. The argument of the logarithm is what it's trying to turn into, and the answer to the logarithm becomes the exponent on the base. All right, so hopefully you're seeing that the numbers always go into the same positions. This one always goes here, this one always goes here, this one always goes here. Okay, so questions on any of these?
Do you need to write log 4 and log 64 to put it in the equation? Or can we just do it by?
Oh, so yeah, let me do one with a fraction. So let me jump over to letter G. Okay, so log base 7 of the fraction 1 over 343. Okay, so even though this is a fraction, it's still a number, so we can apply the change of base formula again. So log of the entire argument gets divided by log of the base still. Okay, so we can type this in, log of log 1 over 343 is the top part, divided by log of 7 equals -3. Okay, so then now that we know that, again, these three numbers, you just got to put them in the correct place. The base is 7. It's trying to turn into this entire argument of 1 over 343. And the exponent which accomplishes that is -3. Okay, so yeah, even though there's a fraction involved, it's very similar. Okay, so questions on anything else? Like, yeah, like you can't just write this part if that's what you're asking. This part? Or this?
7 over.
Here I asked you, no, well, no, you don't have to. This is how we typed it into our calculator though, which is why I wrote it so you could see it. But you don't need to write it out. Okay, so I'll post the answers to the rest of this page on Canvas in case you'd like to check. But let's go ahead and move over to today's handout, please. The one labeled 6.0D. Okay, so there's some properties for logarithms that we're going to discover. Okay, so we're going to go ahead and just jump over to part B over here. Okay, so you have two separate logarithmic terms with the same base. So there's a property that allows us to combine them. Okay, so when you have log base b of m plus log base b of n, you can combine these two separate logarithms into one term. So you keep the log base b part, and you take the two arguments, and you multiply them together. Okay, so please make sure you have this property written down because we'll be using it. Okay, so jumping back over to part A now. So log base 2 of 4 plus log base 2 of 8. So again, you see we keep the log base 2 part, and we're just going to multiply this argument times the other argument. Okay, and then you can just simplify like normal. 4 times 8 would be 32. Okay, same thing over here, log of 100 plus log of 1. You keep the log part, but you would multiply this times that. Okay, so 100 times 1, though, stays 100. Okay, and this even works with natural log, ln, because natural logarithm is still a logarithm. So again, you just keep whatever type of log it is. In this case, it's a natural log. And you multiply the two new arguments together. Okay, so the same thing applies even if variables are involved. So if we look down to part E over here, all right, we want to combine these two together. So we're going to multiply together this argument times that argument. Okay, so when you multiply these, you just multiply the coefficients together. 12 times 5 is 60. And then x times x is x squared. Okay, so go ahead and try letter F, please. The instructions are to condense, meaning combine into a single logarithm. So hopefully what you did is you kept the type of logarithm. So it's still going to be a ln, a natural log. But then you would multiply 4y by 5x. So again, you just multiply the coefficients first, and then you multiply the variables. So x and y are different letters, so they don't combine. You just keep both of them. So we do typically put the variables in alphabetical order. So if you put yx, please just know that we would want to instead write it as xy. Okay, but we can also look at this property sort of in reverse. Okay, so instead of combining these two into a single logarithm, sometimes it's beneficial to split it up, right? We could split this back up into ln 4y plus ln 5x, for example. All right, so over here, log base 5 of 7x, we could split this up because 7x means 7 times x. So we could split this up into log base 5 of 7 plus log base 5 of x. Okay, so again, you can take an argument and split it up into two things that multiply to it. Okay, so why don't you go ahead and try applying that to letter H, please? Does anyone recognize that sound? Okay, so 11y is 11 times y. So we can split this up into log 11 plus log y. Okay, so that's the what we call the addition property of logarithms. We also have a subtraction property of logarithms. Okay, so when you subtract two logarithms with the same base, you can combine them not by multiplying the arguments anymore, because it's not a plus. Because it's a minus, it switches from multiplying to dividing. Okay, so it would be the fraction m over n. Okay, so again, over here, you keep the type of logarithm, so you keep the natural log, but then you take the first one divided by the second one. Okay, so now within the fraction, if you can simplify, you should go ahead and do so. So for example, back over here. So first you combine it to 10 over 100. Okay, but just ignoring the log part for a second, the fraction 10 over 100 can be reduced. You can divide by 10 over 10. So you can simplify it to log of 110. Okay, so please take a minute and try letters A, E, and F. Okay, so letter A, you first combine it to log base 3 of 9 over 3. And then the 9 over 3 part, 9 divided by 3 is 3. For letter E, log base B of 2/4. You can reduce the fraction 2/4 into 1/2. And then over here, 7 divided by 7, that would just become 1. Okay, so as above, we can do this in reverse also. Sometimes it's useful to expand, meaning split up into two different logarithms. Okay, so if you have like a fraction looking thing, that means it's numerator divided by denominator. Okay, so we can split up this single logarithm into log of the numerator minus log of the denominator. And you keep the same type of log. So this one was common log, so that's why there's no base. It's invisible 10. Okay, so go ahead and try applying that to letter H, please. See if you can split that one up into two different logarithms. Okay, so the key thing here, make sure you kept the base 4. If you just wrote regular log 17 minus regular log x, that would not be correct. You have to keep the same type of logarithm. Okay. So any questions about this property? All right. So we have one last property to introduce. So logarithms can have a coefficient, just like how you can have a number in front of x. You can have like 3x. You can have a number in front of a log. Okay, so the way that we can rewrite this, can you stop crinkling that? Thank you. Okay, so this exponent can move up to become, oh, sorry, I said that backwards. This coefficient can move up to become an exponent on the argument. Okay, so this can turn into this. Okay, so looking back over here, this 3 log base 2 of 4, which means 3 times log base 2 of 4, we can rewrite this as log base 2 of parentheses 4 to the 3rd power. Okay, so make sure you see that this is not the same thing as this. The exponent does not affect the entire logarithm. It only affects the argument, the part inside the parentheses. Okay, so again, this is not correct. Okay, and then we can just go ahead and simplify this like normal. 4 to the 3rd power, 4 times the third 4 would be 64. Okay, same thing for letter B. You can take this 2 and make it an exponent of the 1000. So 1000 to the 2nd power would be 1 million. Over here, again, you just make the coefficient turn into an exponent. So this time we can't really simplify, right? Because e to the 2nd power, if you type that into your calculator, you don't get a nice number. That it's a irrational number that goes on forever without repeating. So you just leave it as e to the power of 2. Okay, so I'm going to ask you to try letters E and F. So here, when I say condense, I basically mean get rid of the coefficient by moving it into the argument. Okay, so go and take a few seconds and try those 2 out, please. Okay, so hopefully what you did here, you first move the 2 onto the 5. But if you stopped here, that wouldn't be considered simplified because we can simplify 5 to the second power. That would just be 25. Or okay, and then for letter F, again, we can move the 3 up. Yeah, so you might have noticed whenever the argument has like a exponent, we put parentheses around it just to make clear that the exponent's on just the argument, not the whole logarithm. Okay, and then for letter G and H, we sort of are going backwards. Here, we already have an exponent, so we're going to do the opposite. We're going to move it in front as a coefficient. Okay, so here we can take the x's exponent of 3 and move it in front. Okay. So the 3 properties that we learned on this front page, now we're going to sort of combine them and use them all together. Okay, so on the back, there's one important thing you need to know before you can start combining. You must turn coefficients into exponents. Before combining. Okay, so you cannot, for example, do 3 minus 2 is 1 or 2 plus 12 is 14. It doesn't work like that. Before you combine any 2 logs together, you look at each log one by one and get rid of any coefficients. Okay, so doing part A, again, and before you try to combine these together, just look at the first one. Okay, and you see that this one has a coefficient, so we need to get rid of it. Okay, so we get rid of it by moving it into the argument. And again, this has nothing to do with the other one yet. We're just focusing on this first term. Okay, and then 2 to the third power, 2 times the third, 2 is 8. Okay, and now we look separately at the second term. Again, ignore the first term, just focusing on this one by itself. We see it's got a coefficient, so we move it up. Okay, don't forget we have a minus sign between them. Okay, now that neither term has a coefficient, now we can look at them together and combine them. Okay, so we need to remember what's the rule for combining with subtraction. If we don't remember yet, we can flip back to the front. When you subtract 2 logarithms, you divide their arguments. Okay, so don't forget to keep the same type of log. So it's not just regular log, it's log base b. And then you divide the first argument by the second argument. Okay, and I'll do one more with you over here. So this one has three terms, but you still just go one by one. Okay, the first one does not have a coefficient, so that one's fine. The middle one also doesn't have a coefficient, great. But this last one does. Okay, so we need to move the 6 up here. Okay, so now we can go ahead and combine them together. So when there's 3 numbers to be added, you just add the first 2 and take that answer and plus the third. Okay, so first I'll combine these 2. So log base 6 of x plus log base 6 of y, right? You would keep the log base 6, and then you'd multiply x times y is xy. Okay, and then now that we're here, we can repeat, right? Because you're still adding, so you take the first argument times the second argument. Okay, so I'm going to give you some time to practice this. If you have any questions, please raise your hand. So first, you would want to make both coefficients into exponents. And since this one is an addition of logarithms, the way you combine it is you multiply the 2 arguments. Over on letter D, so I'm just going to go ahead and combine these 2 right away because neither one has a coefficient. So you keep the log base 3, and then you do 12 times 7 would become 84. Over here, you would move the 4 up and place it on the 5. So 5 to the 4th power is 625. And now you can combine these. Again, it's an addition, so 84 times 625 would be 52,500. Over here, I already showed you that we can rewrite the divide by 2 as times 1/2 instead. We would do the exact same thing for this one. Okay, so when you move the 1/2 onto the 11, that becomes the square root of 11. And this is still there. Okay, so we would multiply these together to get log base 2 of 5 radical 6. And now we combine this and this by multiplying 5 radical 6 times radical 11. So the 5 has nothing in front to affect it, so it just stays a 5. And then radical 6 times radical 11, you just multiply the insides. So radical 66. Okay, and then lastly over here, 3 applied to this 3. A new argument of 27. This 2 applied to the 7. 7 to the power of 2 becomes 49. And then this one is subtracting, not adding. So instead of multiplying the 2 numbers together, you would divide them. Okay, so let's look at this last section. Okay, so this time we're going to expand. So, expand means kind of spread out. So instead of combining multiple logarithms into one, I would like you to take a single logarithm and split it up. Okay, so for this first example, we see the fraction bar in the argument, which means divided by. Okay, so we know that subtracting is what leads to fractions. So we can start by splitting this one up. You keep the same type of logarithm, so log base 7, but the numerator becomes the first argument minus the same type of logarithm with the denominator as the second argument. Okay, and then when we're asked to expand, we're going to go ahead and take the exponent and move it in front as a coefficient. Okay, let me actually jump down and do letter C next. Okay, so this one, we don't see any division, right? We don't see any fraction bars, but we see multiple letters. Okay, so we know that when there's multiple letters, that means multiplying. By the way, it's a little confusing. The 3 is not on the Z. The 3 is the index of the radical. Okay, so first we would split this up into log base 3 of just the Z part. And then when you multiply the arguments, remember that's adding, not subtracting. So plus log base 3 of this part. Okay, so this part is fine. There's no exponent, there's nothing to worry about. So we'll keep this part the same. Okay, so this part, it doesn't look like there's an exponent that we can work with, but we need to recall that radicals can be rewritten as fractional exponents, right? So I mentioned above that 6 to the power of 1/2 equals the square root of 6. But in more general terms, a to the power of m over n equals the nth root of a to the power of m. Okay, so how that applies to this problem is the cube root of xy is equal to xy to the power of 1/3. Right, the 3 becomes the denominator. Okay, so I'm going to rewrite this with a fractional exponent. And the reason we do that is so that we can move the 1/3 in front. Okay, so it doesn't affect this one. This one did not get affected. But the 1/3 moves in front. Okay, but we can now split this part up further. X and Y are different letters, so keep this part the same, that part's unaffected. Okay, so the tricky thing is the 1/3 affects this entire thing. So even though we're going to split the X and the Y up, the 1/3 affects both parts. Okay, so the way I'll represent that is I will make a big set of parentheses, right? Because the 1/3 is multiplying the whole thing. Okay, and inside the parentheses, I'll split up this logarithm. Okay, so when two arguments are multiplying, you can split it up into addition. Okay, and then finally, I can just distribute the 1/3 out to both terms. Okay, so